I am Gary from 강원 National University Programming Language and Machine Learning Lab. Today, I will present to you my review about the paper with title, A New Era in Software Security Towards Self-Healing Software via LLMs and Formal Verification. Actually, this paper combines the software model checking technique with LLM. So it's pretty exciting research area. Actually, this paper is a part of actively ongoing project. If you see these links, this is a CV from among the authors which are listed in this paper. So my presentation outline looks like this. First, I will introduce you about what is bug, what are the techniques to detect and fix bugs. Then we'll see some motivational examples. Then on the second section, we'll see preliminary works. You can consider it as related works or just some basic frameworks to the proposed work in this paper. We'll see what is bound model checking BMC, what is LLMs, and LLMs which are utilized in this research work. On this third section, we'll see methodologies, architectural details, and implementations. Fourth section, we'll see experiment and evaluation results. Finally, I conclude my presentation. So as I think most of audiences in this session is a programmer or programmer-related task developers. So in programming, there is bug, it's obvious. So if there is bug, we can encounter software vulnerability. The worst one also, data loss. If there is data loss, it's the very worst thing. So entire program can also crash. So previously, there are traditional methods like classical static analysis techniques to detect the bug, but there are problems with these techniques. False positives are too much cumbersome for developers. Developers can be busy with false positives. The state-of-the-art recently ongoing deep learning techniques also good for this task, but as we know, deep learning is dependent on the previously seen data, so there may be some incorrect results in the case of APR, automatic program repair. So among the deep learning state-of-the-art models, LLMs are just obviously very actively ongoing research topics. From those LLMs, ChatGPT is the one very known and recently active chatbot. So I think most of you are using ChatGPT. So ChatGPT have pretty much best accuracy and performance from all the models. So even ChatGPT have encountered with some defects in the case of APR. It cannot determine or detect or repair programs with non-deterministic values. Non-deterministic values means values intended by random value. So in this paper, the approach is combining the symbolic bounded model checking or software model checking technique with LLM. Especially this researchers of this publication, this paper are combining it with GPT 3.5. We'll see on the practical demonstration on the experiment. But we can use also Falcon, StarChat Beta. So in this case, it's expected that it enhances the quality and speed of program repair. This is the highlight overview of the framework. Users enter a source code to the BMC module. We'll see what is BMC in detail on the next section. So BMC module will check whether the program have some property violation. In program verification research area, program will be checked based on the specified properties. The developers specify some set of properties. A program, a particular software which are developed by any program will be expected to have some properties. Property 1, 2, 3, 4, 5. Just we list down some properties or some behaviors. So the BMC role is to check whether those behaviors are passed throughout this verification process. So if the verification is successful, this verification successful will be notified to the developer. If something is violated, property violation will be notified to the developer. So in this framework, the three typical steps are just taking the input to BMC. BMC will check the property violation. If there is property violation, it will be forwarded to the LLM module. In this case, since we are talking about ChatGPT, the user will add its own specified prompt, or we can say chat text, plus the original code along the property violation, or we can say BMC module outputs. Then we know that LLMs are very excellent in text processing or identifying the text semantically. So LLM module will infer on those inputs. Then it will correct the code, or we can say modified code. This modified code will be sent back to the BMC for further checking. If this program is correct, it will be verified as successful verification. If not, this iteration or this loop will continue until the bounded limit or until the set of limits set by the user will reach. So here are the contributions of this paper. First, the authors have explored the potential of generating and repairing software vulnerability with respect to ChatGPT, or we can say GPT models. So in particular, these authors are focused on memory safety property in C programming language only. They adjust the software verifier for GPT. We know just as we know, just GPT models are pretty excellent than any other models which are interacted in chatbot version or in other tasks. So they adjust software verifier for this, which is ESBMC. We'll see later what is ESBMC. The authors have created 1,000 C programs which can align along their experiment. So this experiment combines BMC and LLM. So they concluded that they have successfully verified the buffer overflow and pointer dereference failures with 80% success rate. So the authors have stand with two main questions: whether the GPT models are capable of producing compilable and semantically correct programs, all about code generation. And the second typical question is just, can the external feedback, in this case, you can consider external feedback means the feedback which is given by the bounded model checking module. So they check whether the external feedback to the GPT models can enhance or improve the bug detection and patching ability of the GPT models. Let us see some examples here. Before I proceed to the motivation example, if you do have any question in this framework architecture or other contents of this presentation, you can raise. So when we see this example, this is a C program language. Just it's very simple code snippet. So if you see here, just it looks like the syntax is pretty good. No problem with the syntax, but it have its own defect on buffer overflow. We'll see later what is the problem. But they text, they chat with ChatGPT in this way. Is there any problem with this code? So ChatGPT reply in this way. There is no problem with this code. The code correctly calculates the value of z as square of y, and then calculates the value of r as s divided by 1000. Finally, the code prints the result of r to the console. The calculation do not result an integer overflow or any other issues, and the program should run correctly. ChatGPT have denied, even typically it have referred, there is no overflow here. But it's obvious this program have the overflow problem. Then the authors of this paper have reformulated their prompt, and they modify their prompt in this way. Is there any overflow in this program? Then the LLM reply is in such a way. It computes all the results throughout this computation. It's pretty much correct result, but it doesn't even point out the integer overflow still. It says there is no integer overflow. The same way I have tried to find out the results or the prompts from ChatGPT as well as Copilot chat during January 9. I have issued the same prompt, the same with the authors they have used in the paper. So in this case, it points out something format specifier. ChatGPT have identified some format specifier. It's obvious. Here the D is just is not comfortable for unsigned int. So that's good. They have ChatGPT have identified this format specifier. It have also pointed out some possible overflows. When we came to Copilot chat, the same day I have tried to ask Copilot chat with the same question, with the same line of code. So Copilot chat have explained all the problems throughout this source code, and it gives me the same correct code which have been solved by this framework, by the proposed framework in this paper. So in this case, just we can raise we can raise 3 reasons for this update from ChatGPT as well as Copilot. First, there is big difference between Copilot and ChatGPT. ChatGPT is a general language model. Copilot chat is specified for software tasks or source code related tasks. So I got the corrected code from Copilot chat due to that reason. And also the reason possible overflow explanation from the ChatGPT, as we know, GPT models, especially the state of the other recent models, which are not publicly released for free, they update themselves just by the approach so-called RLHF, reinforcement learning with human feedback. So the publication of the this paper, actually, it was posted on arXiv. Since that season until this time, just ChatGPT, personally, I believe that ChatGPT can update itself throughout time. So the third reason is Copilot is powered by GPT version 4. ChatGPT, as my knowledge, just the ChatGPT which was released for free is GPT 3.5. So that's also a typical difference between these two results. So this is very exciting example. I have provided here for C language data types for those who are new for C programming language. When we say buffer overflow, these are the range of data types which can accommodate within memory storage. Here the unsigned int have range of this with this specified the percentage u with format specifier. Int data type have such range of values. So when we say the buffer overflow in this context, the computation of the z, which is square of y, is out of this range, out of the unsigned integer value, which is shown from this screen. So you can refer this from the GIGS2GIGS website, by the way. So I will proceed to the next, the solution which was provided by the authors of this paper. The LLM in this case have combined with BMC outputs. This is the output from BMC. It says violated property on file test.c is file name of the source code. Just we don't need any of fault localization or location of the line number. The BMC itself gives us the line number which encounters this error. Then it have the description of this error, function on main function, arithmetic overflow, on multiplication operation, the operation which multiplies y with itself. So it replies also the description of this error. The issue is an arithmetic overflow on the line int z is equals to y times y, blah, blah. Here, these all descriptions are after combining the prompt of the user with BMC outputs. And also it prints out the correct code of the proposed framework solution in this way. So in my local machine, I have tried to run both the vulnerable code as well as the corrected code. As you see from the screen, the expected result will not be negative, but the as you see here, just is an intended result, it's misleading result because the overflow encounters to have such a result. If you run the corrected code, it gives me in this way. So let me see what is BMC, bounded model checking. BMC is a formal verification technique. Formal verification techniques means just these are just techniques which are mathematical forms. So in the case of BMC, the program is represented as transition system, which is a representation of the program. Actually, this representation came from control flow graph, CFG. So it checks every of the transition or every of the state of the program within certain bounds. In this case, the bound is represented by K. So it stands from the initial state. It checks the transition, whether there is problem or not within the transition from one state to another state throughout all the states of this system. Then it combines it with the negation of phi. Negation of phi here, it means the violation of any property throughout the particular states of this system. So if this result satisfies, it is expected that there is vulnerability with this program. If there is no satisfaction of this equation, or if this condition is not satisfied, we conclude that there is no vulnerability with this program. So when these scholars have designed their framework, they have used LLMs. If you refer the documentation of this framework. The GitHub repo have identified two groups of LLMs. The first group is GPT models. In this demonstration, we need OpenAI API key. The second group of models are just the models which are released for free in Hugging Face. Here also we need Hugging Face API key. So you can try on your local machine for demonstration. But here they didn't include the Falcon 7B and StarChat beta on their results because the experiment results of these models is very misleading. It's not performing as GPT models. That's why we are focusing on GPT models. So the methodology is building self-healing software via LLMs and formal verification methods. This framework actually is referred as ESBMC-AI. It is an AI-powered automatic program repair framework. ESBMC means efficient SMT-based context-bounded model checker plus GPT 3.5 in this experiment. So sometimes also they referred it counter-example guided repair framework because it takes a counter-example from the bounded model checking module along with the user's prompt to decide to generate the correct version of input code. So why we are preferring ESBMC in this experiment? There are three reasons in this case. First, as you see from the graph, this is the y-axis is time taken for each verification tool. This is a score. So these research authors have preferred to have fast performing model for their experiment. So within 10 seconds, if you see this red line, the ESBMC kind verification module have fast identification of verification. So they prefer that to select this verification tool. Second, ESBMC supports multiple languages. It can support C language, it can support C++, Python, Java, etc. Another reason is as we refer from the large language research area, we mentioned the state-of-the-art modules, right? So in this case also, in the program verification research area also, this ESBMC is referred to as state-of-the-art model verification or program verification tool. Due to such reasons, they have leveraged this tool for verification of their input programs. If you don't have any question until this point, you are welcome. Okay, I will proceed. Here, this is the details of the architecture of this framework. Here is ESBMC, the AI model. There are two modes of interaction with this framework. One is a user chat mode. Second is solution generation mode. In the user chat mode, the users can interact some general questions, something like how to understand the problem of the input program and some general questions. But using this chat prompt, we interact with the framework in general. Is there any question? Okay. So in this case, the user can generates solution or generates the correct code by invoking some program repair specific commands. In this case, we'll see the later code snippets. They use fix hyphen command for fixing the specified program. So in this case, as you see the this descriptions, the bolded one is just like request. The later one is response. For example, here, if the user is going to request the output from ESBMC, just it will interact with the framework. The ESBMC will reply the output of the source code. Then along the source code and the SPMC verification results, the user will ask the AI model. Then it can also ask some questions. The model can also reply some explanation about the source code as well as the SPMC response descriptions. Later on, it can invoke the fix commands. If the fix command is invoked to the AI model, the AI model is expected to generate the corrected code. If the corrected code is tested by the ESBMC tool, then it will be verified as successful verification, as we see on the previous overview of this framework. So totally, the interaction between the user and the framework is in this way. If you have any question, you're welcome. Okay, here, as I have explained on the previous slide, we can ask some questions about the purpose of this model, about the problem with respect to this code, and also some vulnerability occurs in more detailed. So here, the solution generation mode is going to done by this command, fix code. If the user issues this command, it's totally requesting the AI model to generate the corrected code. So the AI model also expected to reply only source code, no need of natural language texts. If there are some very concise NL texts, just it can be processed by string pre-processing techniques. This is sample implementation on the user mode chat as well as solution generation mode. Here, we take the ESBMC output as input of the verification module. Then the chat object will contain the message from user as well as the original source code and the ESBMC output. The response will be just loading the chat prompts, then printing back to the user. Here, we should have to focus here. If the user is issuing this prompt /exit, it is exiting to, from the prompt of the framework. Actually, I have tested this tool from my local machine. If you issue this command from the prompt of the framework, you automatically return back to the
겔의 목소리가 안 들립니다.
잘 들리시나요?
또 작게 들리는데요.
들리시나요? 지금?
예, 작게 들립니다.
네, 죄송합니다. 어, 헤드폰을 배터리가 꺼버려서 지금 잘 들리시나요?
아니요, 작게 들립니다, 여전히.
어, 네, 지금 잘 들리시나요?
네, 아까보다 잘 들립니다. 네.
네네네, 죄송합니다. 불편 드려서.
네, 진행하시면 될 것 같습니다.
아, okay, sorry for the interruption. So here we use this fix code command to generate the corrected version of our vulnerable code, which was sent to the LLM model. The second figure here is just about solution generator mode, how the LLM model can generate a solution for us, the corrected code. So the model will, the user will set some certain attempt limits. For example, here it was assigned to 10 attempts. Based on this range of attempts, the LLM model will try to generate corrected codes. So after generating the certain code for the corrected version of our vulnerable code, the ESBMC verification module will verify the generated code by the LLM. So here, the ESBMC will expect to have two parts of output. First is the status of the verification, whether it is okay or not. The second one is the actual code or the actual output. So here, if the result is okay, this framework ESBMC-AI will give us the correct code. The user will receive the correct code unless some failure message will be printed out to the user. In this way, way, the verification and generating corrected version of the code will undergo. This one is just it's nothing but about extracting the source code only from the output of the LLM module. Here, the LLM give us such preceded with such short texts. For example, here, certainly here is the corrected code. Then it can insert it with such marks. So in order to remove the unnecessary text, we use the letter code. This the code under this line is just, it is for removing unnecessary characters or strings from the output of the LLM. So in order to have good verification from this framework, the authors have pointed out some tips. First, the message should have to be direct and concise. They recommend 500 tokens in size. They recommend also just to use some instruction about the AI model's purpose. what purpose is expected from this model, from this AI model. This instruction should have to have consider such keywords. Let's say they recommend that to use such words: you shall not, instead of you may, you might, you may not. And also you should have to request the LLM model to reply as okay if it understands our instruction. Here are the experiments of this framework. They generate C program. Actually, this framework have good approach for us. We know the GPT models are just black box. We don't know what is going beyond ChatGPT. We can only interact with ChatGPT. Even I have tried fine-tuning, just paying some amount from the API of GPT. So even they couldn't show us the source code of our fine-tuning. They give us only results. So personally, I believe that such practice is good for us in order to interact, in order to apply the GPT models on such interesting applications, especially in API. It's very interesting because ChatGPT models are very efficient and excellent than any other models. So they generate the program from GPT 3.5 and the code correction also using GPT 3.5. So they generate the code generation using this hardware specification. Actually, I never been used such hardware device. That is very powerful hardware. The code correction is done on single 2070 MacBook Pro equipped with 16 GB RAM. So in this case, the code generation have done in this way. They use a GPT 3.5 turbo model. They generate 1,000 samples of C language. And also they use such strategy to generate minimum 10 lines of code, maximum 50 lines of code. They use to give them just at least two functions to use strings, arrays, bit manipulation, string manipulation inside their code. They instructed it to be creative, to include every necessary headers, because if you are familiar with C programming language, there are there are directives which are start by include. And also they say just no including the comments within this code. In this case, they have achieved compilation success rate 93 up to 73%. Later on, they use their IDE. They compile their generated source code. If the source code have some errors, the GCC error or the compiler error will be fed back to the LLM. Then they have achieved 99.9% of compilation rate. So in this way, in this case, they have got the typical question for research question 1. They have concluded that due to the use of GCC error output, just we can say actually here, just compiler feedback. They use compiler feedback to achieve 99.9% of code compilability rate. On the second experiment, just it is about the verification of the code using ESBMC. They generate 1,000 C language, as I have introduced you on the previous code generation. So then they categorized it in 4 categories. The first category is buffer overflow. This problem is occurred by the scanf function in C language, actually. For those who do not know about C language, scanf means just you can take it as input function in Python. So due to the scanf, such instances are categorized as buffer overflow, 350 samples as verification successful, 123 just as other vulnerabilities. Actually, the pointer dereference failure is under this category, other vulnerabilities. 114 category as verification unknown. In the case of verification unknown, if you refer to the paper, just they consider that 10 seconds as maximum limit of their verification process. If any program is exceeding this 10 seconds verification limit, they skip it. So the particular program with more than 10 second verification process will be considered as verification unknown. So in this case, just sample vulnerable C program. If you see here, just the line scanf percentage is, this line is the serious vulnerable line. Here, just it takes the inputs of a user. Maximum limit of this input is 10. In the case of C language, after we enter our input, C language adds another extra character or string terminator. It's called null terminator at the end of our string. So if it is occupied all the 10 space memory space of the input, then the null terminator will be 11th character or 11th string to our input. So the buffer overflow will occur in such a way. So if you consider this ESBMC model verification output, it describes all the properties, all the verification details, the error trace, just the counterexample details, just the file number, line number of this vulnerable code, the cause of this violation property. So in this way, just it will show us the details of this error. Later on, if you request the ESBMC to fix this error, only one character or only one symbol will be added to this line. They add 9 here. This line of code or this string limits the output to be 9 memory space for the input user. Then the remaining 1 space will be left for the null terminator or the string which is added by the C program by default. So in this way, they repair 16 out of 20 such buffer overflow problems. Then they have also repaired dereference failure issues, which are listed down here. These are the name of files which they have selected randomly for the dereference failure issue. So they conclude that 14 out of these samples have been fixed with this strategy. In general, just we can conclude that 80% of the samples which have selected for this problem have fixed using this framework. When we see the comparison between the state-of-the-art models, which are focusing on bug detection and repair approach, they have compared based on these categories, whether the tool is detecting, whether it is repairing, whether it leverages the BMC, whether it supports LLM. So if you have seen from, if you see this first column, almost all the bug detection tools are capable on detection, but some of them do not repair. The ESBMC-AI framework, which are discussing right now, is capable of repairing particular programs. It leverages bounded model checking tool, and also it uses the LLM. It supports LLM models. Any LLM model can be leveraged for this experiment, by the way. If you refer their GitHub repository, just they can, this framework can be capable of using any custom model, but the built-in models already stored on their repository is just the GPT models as well as two Hugging Face free models. There are also some treats for validity of the framework. If you see here, just this framework is highly dependent on LLM understanding of code semantics. If the model is capable of understanding the code semantics with excellent capability, the model will be good on the automatic program repair. If not, it will be just non-efficient or performance will be low. So that's why they reject the free models and they focus on GPT models on their experiment. This also just can undermine the program's real-world behavior. Any programming language have its own real-world behavior, so such scenarios will not be considered if it is dependent on the LLM model. It can generate also programs which are syntactically correct but not effective on bug fixing. So some issues with respect to verification process also. This verification is adding some other bottleneck on the framework because any program will not pass to decide whether it is correct or not before passing through this verification process. So this will add some bottleneck for the framework. Some complex structures like loops, multi-threaded programs can impact the efficiency of the framework, but some recommendations have been suggested by the scholars of this paper. First, they recommend us to analyze sections of programs, piece of program, for example, individual functions, some sections of program, and also to have small segments of code for our verification. They recommend to use up to 100 lines of code. In case of arithmetic overflow, like we have seen on the previous example, just we should have to use built-in values instead of non-deterministic inputs. So when we conclude our presentation, this framework is the combination of LLM, particularly GPT, with the formal verification method to enhance or to improve automatic program repair. They have achieved 99.9% code compilability based on the code generation strategy they have employed in this experiment. They suggested that high compilability rate in the generated source code means they have good confidence on code repair process, which is sent to the BMC for verification. And also they tried to fix buffer overflow and dereference failure with 80% success rate. Here are also the some pros and cons of this framework. Actually, integrating such LLMs with formal verification or other software engineering, static or dynamic tools is very exciting and future open research approach. Even personally, I'm so interested on working in such research. So it have good, pretty opportunities. It is very fast and more accurate on bug fixing. It ensures software reliability, productivity, and security, but it have also some limitations. There is a need of massive computational resource. It may introduce also some unintended vulnerabilities and also overfitting. These are just some points which are pointed out from this paper. If you don't have any question, You are welcome. I have finished my presentation.
네, 수고하셨습니다. 질문 부탁드립니다. 이 논문은 아직 퍼블리시가 안 된 거죠?
네, 아카이브에 올려 있지만 publish 되는 건 찾을 수 없어요.
네, 감사합니다. 그리고 아까 GitHub 레파지토리가 있다고 말씀하신 건가요?
네, 맞습니다.
그러면은 뭐 커스텀 LLM 그다음에 커스텀 베리파이어를 그냥 사용해서 바로 돌아갈 수 있게 구현이 공개돼 있나요?
네, 커스텀 베리피케이션 도구가 관련해서 전부가 없지만 커스텀 LLM은 할 수 있다는 건 공유되어 있습니다.
네, 감사합니다. 답변하실 때 영어로 답변하셔도 됩니다.
네,
컴파일 에러 고치는 거는 컴파일러 피드백으로 한 것이고, vulnerability를 이제 고치는 거는 이 BMC 툴로 한 거죠.
네, 맞습니다.
그럼 99.9%의 코드가 컴파일이 된다고 하는데, 그럼 0.1% 실패한 거는 혹시 어떤 코드인지 언급이 돼 있나요?
그건 자세하게 없지만, 아, 그런 방식으로 사용하였을 때 이런 식으로 컴파일레이션 성능이 높았다라는 거 있습니다.
아까 전에 컴패리즌 했던 그 테이블 있잖아요. 그,
Yes,
그
yeah. 네.
모델들이랑 같이 같은 벤치마크에 대해서 성능 비교를 한 건 없나요?
어, 제 생각에는 그 절차들이 이런 they have compared based on these uh, issues, whether they detect or whether the model is repairing, whether it is leveraging BMC, whether it is leveraging LLM. But in this model, there is no specific benchmark. They use GPT 3.5 Turbo to generate the C language source codes. Then they use their compiler to check whether the generated code is compilable or not. Then they send it to the ESBMC for checking whether the generated code have some runtime error or not, or some vulnerability error or not. If this source code is verified by the verification tool, they consider that the generated code is free of any vulnerability or free of any runtime error. If it have encountered vulnerability error, they send it the instruction tuning experiment will be the user's text, something description about the error, about some purpose of this interaction with the LLM model. Then finally, attaching with the BMC's output, as we have seen on the as we have seen in this here. So there is no specific benchmark in this experiment.
그 벤치마크라는 게 그러니까 여기서 근데 최초 입력은 코드 아닌가요?
네?
그러니까 최초 입력은 코드고 원하는 거는 그 vulnerability나 컴파일 이슈가 없는 코드를 생성하는 거 아닌가요?
음, 그 코드는 원래 있었던 코드 아니고 그냥 LLM 좋았던 코드만 쓰는 편이에요.
LLM이 생성한 코드만 쓴다고요?
네, 네, 맞습니다.
근데 제가 잘 이해가 안 되는 건 피겨 1을 보면 유저가 테스트 코드를 이 프레임워크한테 주는 걸로 시작하는 거 아닌가요?
그거 예시로 제가 하는 것 같아요.
아, 그럼 LLM한테 초기 코드를 생성하게 하기 위해서는 어떤 프롬프트를 주나요?
네, 프롬프트 이 교차들이 프롬프트 생성 생성하는 프롬프트 쓰셨을 때는 이런 식으로 쓰십니다.
그냥 아무 코드나 만들려고 하는 거구나. 제가 이걸 놓친 것 같습니다.
네, 네.
이게 무슨 의미인지 잘 모르겠네요. 감사합니다. 그 채팅창에 질문이 하나 올라와 있습니다.
네. 감사합니다. So, okay. Thank you for the question, Takshinu, I think. Eh, uh, I think the main objective of this research is just integrating the state-of-the-art LLM models with software model checking tools. That's the main idea. It's good practice for us. For example, personally, I believe this is good practice because just we are only users of ChatGPT, but we cannot there is no any reveal what is going behind ChatGPT. Even I paid for the fine tuning practice, but uh, they couldn't show us something about the fine tuning code or any strategies. So this is the main idea, just connecting the BMC module with prompt for LLM. Thus, I admit your idea, Mr. Pakshinu. So there is also some prompt templates. For example, I didn't include it here, and they set some prompt templates from their experiment. For example, about temperature, they set some value of temperature for their prompt and other freely adjustable prompt attributes. But I didn't refer in detail, but it's a good question. Thank you.
감사합니다. 혹시 그 음향 문제 때문에 좀 발표들이 지연돼 가지고 시간이 많이 지체됐는데 마지막 질문 하나 정도 받거나 없으면 바로 마무리하겠습니다. 혹시 질문 있으신가요? 네. 질문 없으시면 오늘 좋은 발표해 주신 계래 학생 고생 많으셨고요. 그러면은 다음 주에 뵙도록
네,
하겠습니다.
네,
수고하셨습니다.
감사합니다.
감사합니다. 네.
수고하셨습니다.